So, in the last class probably we have started discussing about this multi-stage space time switch combination. So, what we will do this particular class also will be discussing the same thing. We have left over a particular configuration of TST switch. So, we will continue on the blocking performance of that kind of switch and how do I design that switch. Do that same thing over here. So, let us go back to our design diagram that we have drawn in the last class. So, basically what we have done so far is we have given two connectivity, and those two connectivity how we have configured that also we have mentioned over here. So, basically we have a connectivity of 1 to 4 dash, that is something we have shown already. How do I do that? What will be the exact configuration at the first TSI? So, first TSI I do not move anything. So, I keep it as it is, then I do a cross connectivity in the first slot 1 to 2, and then I actually swap it in the next one and I get to 4 dash. In the second one 3 to 1 dash I want to connect. So, first TSI I means randomly choose, means it should not be on means I should not see what has happened. Okay. So, I should be able to do switching whichever way I wish to do. So, that should be the motto of doing switching. So, basically I choose to swap it in the first this one. So, I put it in the second slot. In the second slot I give a means cross connectivity. Okay. So, that means it goes over here in the second slot, and then I do a further time swapping. So, the third one comes into the first slot and it goes out from 1 dash. So, this is what we have already configured. Now, for the blocking case. So, now I want a connectivity between 2 to 2 dash. Let us see whether I can do that. So, 2's data will be over here. I have no option for this, and if 2 to 2 dash I have to connect. So, 2's data should come over here in the second slot only. So, what option I have at the TSI, because 1's data is already occupying the first slot of after TSI. So, I must put 2 over here. So, there is no other way, I have to do it. So, if this is the case, what I have to do? In the second slot I have to give this connectivity, but that will collide with this data. I have no option now. So, I cannot do a switching for 2 to 2 dash, even though this 2 port and 2 dash ports are free, I am somehow blocked myself because of this connectivity. You might be asking, maybe can we do something? Again, like the rearrangeable non-blocking space switch, we can do something. So, the second connectivity we have made, we might rectify that. So, what we can do? We might rectify this connectivity. Okay. So, this is something we can rectify. So, 3 was over here, I could have put my 3 over here, and then at the first instance what was the switching option? So, 1 to 2. Okay. So, if 1 to 2 I can do, I can also do this cross. So, if 1 to 2 is connected, I can always do 2 to 1, nobody blocks me, because that is the cross connectivity. I can always do that, one input port to another distinct input port, the mapping is being happening. So, I can do that. So, 3 will come over here, and then I at the TSI I do not do anything. So, 3 comes over here, 3 goes out from here, no problem. If I do that switching, now you see I have the option of the next connectivity 2 to 2 dash if I want to connect. So, 2 comes over here, 2 I keep it over here because 2 is free now. Now, at the second, because of this connectivity actually I do not need this connectivity, this was gone. So, now at the second instance I can keep a connectivity like this 1 to 1 connectivity. So, in the bar state I connect the switch. So, 2 goes over here, I keep 2 over here and 2 goes out from here. So, as you can see now, just by reconfiguring the previous connection. So, this is called rearrangeably non-blocking switch, I could take out that blocking state. Okay. So, that means I can randomly, whenever a connection comes, I can randomly give connectivity. I can adjust TSI, I can adjust space switch configuration, and I can give connectivity randomly. So, at that point, whatever looks best to me, like in space switching also we were doing, we just do that connectivity. But whenever there is a blocking situation, I try to see who are actually blocking. So, as you have seen, this connectivity 1 to 4 dash and 3 to 1 dash, these two were actually blocking this 2 to 2 dash connectivity. So, again with the clause argument, like I have told, you see input who are actually disturbing him. So, 2 to 2 dash connectivity, at the input 1 is the disturbance creator. So, this connection 1 to 4 dash, and at the output it is 2 dash. So, 1 dash, this connection was creating disturbance. If there are multiple C's, so all of them, try to see those connections and rearrange those connections, so that you get a free slot over the entire switching matrix and you can provide connectivity. This is something you can do. So, this is called rearrangeability non-blocking. But can I now talk about, like clause has given that argument, can I now talk about a non-blocking switch, strictly non-blocking? I do not have to rearrange anybody. I can give any random connections, as long as those connections are viable, I will still be able to give connectivity to the next one that is coming to me. Okay. So, this is something which I have to try to do. Let us see whether we can do this. So, for that what I need, you remember in the sharing stage. So, where exactly it is getting shared? If you have seen, it is actually getting shared in the middle stage. So, this 2 to 2 dash I am talking about, that is actually sharing this middle stage, almost like that one of the stage, middle stage they were sharing, that is where it is getting shared. Okay. So, you have the, because 2 to 2 dash you have to give connectivity, that means whatever happens they must be, because 2 dash is associated with this TSI, 2 is associated with this TSI. So, it must be occupying some of this first port of the space switch. So, in the first port of space switch, what are the sharing option? We are sharing these slots. So, probably why it is getting blocked, because there are not enough slot. So, I have this C number of input things and C number of output things which are sharing those slots. Okay. How many slots I have? C, that is not sufficient. If I can now give with the similar argument as clause has given, 2C minus 1 number of slots. So, over here my C is 2. So, it should be 2 into 2 minus 1. So, 3 number of slots if I can provide, I will probably see a non-blocking switch. What does that mean? How do I do the connectivity? Let me draw a fresh diagram, then it will be clear probably. So, let us try to see, let us quickly draw that diagram. So, now all I have to do is in the middle stage. So, you remember we had this 2 slots all synchronized, in between we are putting 2 slots. So, within this 125 microsecond now we will be putting actually instead of 2, 3 slots, because my 2C minus 1 is 3 now if C is equal to 2. Okay. So, I put 3 slot over here. At the space switch output also I put 3 slot. So, basically space switch has now within 125 microsecond 3 switching options. Okay. And then from there 2 slot. Okay. So, the TSI is little tilted now, it is not symmetric. So, at the input of TSI, the data slots that are coming, that is 2C minus 1, and at the output of this TSI 2C slots are going out. That means, in 125 microsecond I am reading it faster, because 2C minus 1 over here it is 3 data has to be read, whereas while writing I will be writing little slow. So, I will be writing, so this is C, okay. I will be writing C number of bytes. Okay. So, 2c minus 1 number of bytes are coming in. So, while writing I have to write it faster, while reading at the output I will be reading little slower with c number of bytes in 125 microsecond. So, that is the TSI we will be now designing. At the same time, this TSI is also tilted. It is actually, it has a lower writing speed, okay, and faster reading speed. Over here C with the C bytes are coming at 125 microsecond within 125 microsecond, and 2C minus 1 are being fetched. Okay. So, what will be happening? Few things which will be happening now. One is this TSI, how many locations it will have? This TSI now, TSI memory will be little bit more, because whether you read or write you have to keep data storage of 2C minus 1. So, earlier it was C, now you have to keep a data storage of 2C minus 1. So, TSI will have data storage which is 1 up to 2C minus 1. Okay. So, that many data storage will be there, and then depending on input associated and output random write and sequential read, or sequential read and random write, depending on that what will be your memory, these things that will be dependent on that. Okay. So, where from you will be fetching, that is something which will be dependent. So, now let us try to see if we are fetching them. So, means if we are trying to write them. So, that means what is happening, whatever comes. So, let us say I am designing this switch. Okay. So, 2C minus 1 datas are coming, I am just storing them one after another. Now, there is a control. Okay. So, in the control what I have to do is I have to, how many bytes should be there in the control, because while actually reading them I only need C number of locations. So, therefore, there will be C number of location, but each location how many bytes has to be or how many bits has to be there, because each location should be specifying one of these 2C minus 1. So, that should be log to 2C minus 1. Okay. These many bits are required, and there are C number of locations. So, C into this plus 8 into 2C minus 1. So, that should be the memory requirement of these TSI switch now, as you have understood. So, the TSI switch gets little bit tilted, but let us now try to appreciate what this has given me. Has this given me a non-blocking case? So, earlier if we see, so we had a configuration of, let us go back to that. So, we had a configuration of 1 to 4 dash and 3 to 1 dash. So, 1 to 4 dash and 3 to 1 dash. Okay. So, let us try to do this 1 to 4 dash. So, the way we have done earlier. So, 1 this 1 to 4 dash we will have to do. So, once data comes, now I have 3 options anywhere I can put. Okay. Let us put it in the first slot. Okay. So, I put it over here. Remember the space switching, it cannot do time readjustment. So, if the input to the space switch are 3 slot, then output also should be 3 slot. If it is 2C minus 1, output should be 2C minus 1. So, if I put it in the first slot, at the first slot of this configuration, I can do this 1 to 2 configuration, and I can put it over here. So, the data of 1 comes over here. Okay. Now, I have to put it in 4 dash. So, I do this swapping. Once data comes over here, that comes from here. Good, very good, no problem with that. Now, the next one 3 to 1 dash. So, 3's data comes over here. So, that is 3. Now, over here I might choose to swap it. So, let us say I put it in the second slot. So, that is where my 3 comes. So, 3 then should go over here. So, it will come in the second slot because space switch cannot swap time. So, I have to do 2 to 1 connectivity in the second slot, because in the second slot only I have to push this data to this 3 to 1 dash. So, again this has to be swapped and I put it over here, that will go out from this one. Now, suppose I want to give this connectivity 2 to 2 dash. Now, you can see it is very nice, because whatever I do, I have occupied the first slot and at the output I have occupied the second slot, I still have the third one remaining. So, this was clause argument, that when I am sharing this middle stage only I am sharing. If I have, if there are C number of this one and C number of this one, in the worst case scenario, all other C are coming, C minus 1 are coming from the others, and this one, all C minus 1 are connected to some others, which is happening over here. Okay. So, 1 to 3 dash others and 4 to 1 dash from others, it is coming to this, and then still I am trying to get the connectivity. If I have 2 C minus 1, which is 3 over here, so I still get the last one to be filled up and I can do the corresponding switching, so that I have a strictly non-blocking switch. So, now 2 to 2 dash I can put 2 over here, I can put the 2 after time switch interchange over here. If I do that, I can do this bar connectivity at the last one. So, 1 to 1 connectivity I can do that, because it is free. So, my 2 comes over here, 2 I put it over here, all are free and it comes out from 2 dash. So, this is how I can still make a a strictly non-blocking switch if in the middle stage of TSI I inflate. So, inflation is TSI switch will now no longer have a symmetric input to output. So, if it has C number of slots coming in, I am now having 2 C minus 1 slots going out, but things are all getting symmetric, because in the other side of TSI I will be just doing the reverse thing. So, from 2 C minus 1 in, I am getting C out. Because of this middle stage inflation or expansion of 2 C minus 1, I have all the possibilities. So, whichever way now I do switching, it is strictly non-blocking. I do not have to rearrange anything, I can get any kind of switch connectivity blindly if I keep allocating things. So, this is the beauty of a particular TSI or TST kind of switch. So, first stage T, second stage S and third stage T. Now, if you ask me that what is the overall amount of memory that is required, can you now do this calculation? Let us try to do this calculation. Okay. Let us see what is the memory requirement. In the space switch, what is the memory requirement? Let us say I am doing NC cross NC switch with 3 stages. Let us say in the space. So, now how many slots are there? As there is a expansion, so there will be 2 C minus 1 slots. So, each of these 2 C minus 1, what is the control logic that is required? Control logic, because it is a n cross n switch. So, n log to n is the control logic that will be required, and that is required for 2 C minus 1 slots, because there is a slot expansion. So, each slot must have a particular associated control logic memory, which has to be stored, so that I can do the control at the particular instance. Things are all synchronized. So, I have no issues, every slot means every time slot boundary I go, I do that switching, and next slot I fetch from memory, I do that switching. So, I keep doing this kind of switching. So, from I fetch data from that control and I fed it to the multiplexer, accordingly the switching is being done. Okay. So, it will be keep on repeating every 125 microseconds. So, this many memories are required for doing the space control. Now, let us talk about the TSI. The second stage TSI, you have already seen that 2 C minus 1 number of slots are coming and I am reading C. So, for that I have already calculated. So, it should be C log 2 C minus 1 plus 8 into 2 C minus 1. How many such TSIs are required? 1 to n. So, n number of such TSIs are required. So, that is the memory that I will be requiring. Now, at the input stage, so input stage what is happening? Oh sorry, this is the this memory requirement and data requirement. Now, this input stage switches are little different, because over here what is happening, C number of bits will be coming in and I have to read this 2C minus 1. So, now let us see how much data storage I require. I require C into each one of them are 8. So, C into 8, right. So, n number of TSIs are there, C into 8, that will be the requirement. Now, while reading I still need this whole thing, right. I have to read a particular these things. So, let us try to see how many such memory requirement will be required, because now I have to distinctly read 2C minus 1. So, that requirement will be 2C minus 1. So, there will be 2C minus 1 memory places. So, 1 to 2C minus 1. So, 2C minus 1 memory places will be there, and each one of them what I need to specify, which location it is there. So, that is there are only C locations. So, log 2 C and n such, because there are n TSIs. So, this will be the overall memory requirement of this kind of complex switch. Once I have that, what is the overall delay of this switch? It should be 250 microsecond, because every switching that you do, you need to go through the first TSI and the last TSI. You have to do it, one stage of TSI and followed by the third stage of TSI, you will have to do that. So, therefore, 125 microsecond into 2. So, there will be always a 250 microsecond switching this one time or switching delay that will be happening always. This is the overall complexity, that means, this is the overall memory requirement. What is the space requirement or switching blocks requirement? So, n cross n switch I have done. If I do not do any multi-stage in the middle stage also, so it will be n square, that is the requirement. I can further reduce it if this space switch again I do a 3 stage or 5 stage or 7 stage 9 stage switching, then further this will be reduced. Okay. So, that is something I will be able to do. So, this is possible. So, this is something which we can also do. So, now you have seen how do I do this strictly non-blocking, rearrangeably non-blocking 3 stage switches with combination of space and time switch. So, we will later on also talk about this STS switch. So, let me just draw a quick diagram for STS switch. So, that first stage will be space, second stage also will be space, and in between there will be TSI. Now, again if we just, so this is the space stage, so let us say it is n stages, of course, they are followed by a multiplexer of C each. So, it is a dimension of n C, and then middle there will be 1 to k stage. So, this k again you will be able to prove that if I wish to do strictly non-blocking, this k has to be whatever that number is there, let us say n. So, it should be 2n minus 1. So, that has to be there. So, this is something we will be able to again prove if you wish to do strictly non-blocking switch, because these are getting, this middle stages are getting shared. So, you can do this kind of space switching. So, that is STS switching, you can always do that. Of course, this would be n cross k space switches and k cross n. So, basically the amount of space switching will be much more high, because it will be 2n into k if your k is 2n minus 1. then that is the switching dimension that you will be requiring. So, this will be much higher. So, space switching elements that will be required will be much higher over here. Of course, you will be able to see that memory requirement will be less, but of course, memory is much cheaper than the switching elements. So, there is a rule of thumb that every memory element is 100 times cheaper of this switching element. So, if you combine these two, so if there are one switching element and one memory element, cost of that will be this switching element will be 100 times more costlier. So, okay, so some unit cost if I see that it will be 100 C, this will be only C, one memory element and one switching element. So, this is the cost equation that will be happening. Okay. So, accordingly, if you try to minimize the cost, you will have to see it in this fashion, but of course, over here there is one advantage because only one TSI you are doing. So, it will be always giving you 125 microsecond delay, it will not be giving you anything more than that. Okay. So, that is something you can do. So, now what we will try to do in the next class is try to see can we extend the blocking probability calculation that we have done through Lee's graph to these things also. It is very easy, we can actually do that. So, now we will also try to evaluate the blocking probability of these kind of switches which are space time space or time space time or just TS switch. So, that those kind of switches we will try to see what do I do for evaluating blocking probability. So, Lee's graph essentially can that be applicable similarly over here, that is something we will be appreciating. But next what we will try to do, another switch that we have not talked about so far is a trunk switch. The blocking probability calculation of trunk switch is not as straightforward or as easy as this one. So, we will try to see there are a very rich literature in queuing theory which will be borrowed to evaluate the blocking probability of trunk switches, and those are famously known as Erlang B or Erlang C formula. So, we will try to appreciate what kind of minimal knowledge of queuing theory that we can introduce, so that that can be applied for evaluating the blocking probability of trunk switches. These are actually a typical local subscriber loop or local circuit space switching that we were appreciating so far. So, we will now try to see trunk switch where output can be anything. It does not really matter that we have to go to a particular certain output port, output can be anything. So, they are like server, any of those server I can take whichever is available. So, that is trunk switching for you, and we will try to see whether we can evaluate the blocking probability of that. Okay. Thank you.